Okay, doke. Welcome, friends. It is week 2, lecture 2. We are continuing here with our singly linked lists. We had a riveting office hour on GitHub. Oh, looks like I didn't link these. I'm so sorry. I'll make sure I link these after class. Have them uploaded. I just need to link them. We had a riveting class on Git and GitHub. So we talked all about Git, how the repository works. We linked it together with GitHub. So that way, and we push things to actual GitHub repositories so we could visualize and see how we can do that for our personal projects. We'll keep adding on and talking about that, especially as we get into our group projects, because that's going to be something that's really important. As just a reminder, you can watch this video here, and this is another Git and GitHub tutorial that we can walk through and that you can see just how this works. I'll also make sure I share with you guys, there's a playlist of like Git sessions, that how to handle merge conflicts, how to do all that we have, and I'll make sure that I share that with you guys as well. That way you guys have that, and as you're going into the group projects, you can do that. Cool. A little bit of kind of catch up is, don't forget, we still have discussion questions. You have to do those. Those are open, so please go do those. And as a reminder, if you have any issues where you are posting them and they're not looking like they're showing, or showing that you didn't, just please please take a screenshot and let me know and say, hey, here it is. Here's my screenshot of my post. Here's what it's reflecting I'm not doing it. Either I can verify on my side, but also I can advocate for you and say, nope, they did this. So if somebody were to come to me and say, oh, I see that Austin hasn't done any discussion questions, I can be like, nope, they have, and we're dealing with this. So please make sure you do those. You do have, I know that you guys are finishing your group projects. You do have arrays and strings to do. So please make sure you don't forget about your core assignments. That's still part of it. You still need to be up and compliant. You still have to do 90% of your core assignments in order to pass this stack. So it's not just your solo projects. You have to do these assignments as well. Yeah. And then lastly, again, I need by the end of the day on Thursday, I need to have, if you want, and I got a couple of people, but if you want to be in a group for your group project, I need to know that by end of day Thursday. Please send me an email, CC'd with everybody that is going to be in your group, and say, hey, we would like to be in a group. Once you do that, I can put you in a group. If it's not done by end of day Thursday, on Friday, I will be putting everybody in groups. Once your group is assigned, your group is assigned. So again, if you want to work with somebody, that's awesome. Just go ahead and send me that email. If you don't know or don't really care, feel free to fill this out. A lot of you guys already have. I will be using these to go through and saying, okay, great. I'll pair lots of people with JavaScript or lots of people with Java, or, something of the sort, just to make sure that everything is a-okay. Cool. Awesome there. All right. Great. Okay. A little bit of recap. We've got quite a bit I want to get through today, but a little bit of recap. We talked about singly linked lists yesterday. We talked about how they're different data structure. We talked about sort of the difference in memory that it has compared to like a array. And we built a singly linked list where we were able to connect pieces of data together. And we sort of had to manually build this using this node, kind of node.next value. And we were able to iterate through this. So if I were to run this, we get all of the data, all of the values, and we get, all the different things we have using a while loop, so we can actually see, first name or whatever that is. I added first name here. That's a terrible thing, but we were just doing it to show that it was an attribute. Cool. Any questions or anything that was fuzzy on creating nodes? Again, a node is just a way that we're storing some pieces of information. But any way or any questions on this process right here?
So I have a question
Yeah.
for array. Like you have elements in the square brackets, right?
Mm-hmm.
Different kind of elements. But for single linked list, is that something similar for like array, or is it completely different data structure or data type?
They're different in the sense of an array. good question. An array has, the main things about an array is, no, I thought I was annotating, sorry. Main things about an array is when it stores data, it stores it using, I mean, it doesn't actually store it using square brackets, but it stores it using what version or what does it use to sort of store and identify where these numbers are?
Yeah,
And
back
we're-
to back. Yeah.
Yeah, back to back from a storage perspective, but what, if I wanted to get the number 7, what am I going to use to get that?
Okay. Yeah, different ways of like restructuring or parsing to go to that specific
Index.
element.
Parsing,
Like
but
in-
yeah, somebody said it is the index, right? I can say if index 2, let's say like, let x equal this, I could say, x of index 2, and that's going to give me 7, right? Because then goes 0, 1, 2. So what's unique about arrays is, or what's different about them is they use an indexing, right? Which makes it very fast. This is a O of 1 time complexity. That means a constant time. We saw that, right, when we were talking about time and space complexity. It doesn't matter how large your array is. If I'm just looking at, x can be 1, or sorry, x has to be at least 3 values, but 3 or 3 million, it doesn't matter. It's still just going to go and it's going to grab that value, right? So that's a power behind that. So if you know where things are at or how things are done, great. That is very, very powerful. The difference is when we're dealing with nodes, let's say this was 2, that points to 5, that points to 8, that points to, 12. We don't have an index position. There's no way. All we have is the current value and what the next value is, right? The next version. And so if I wanted to get the number 8 here, what do I have to do?
So I need to connect first from 2 to 5 and from 5 to 8, like a node.
Yeah. Yeah, right. I have to go and I have to go through 2 and check. Does this have it? Nope. So then it goes here. Does this 8? Nope. So then it goes here. Is this 8? Yes, it is. Okay, great. I have it. Now, when we're dealing with time and space complexity, what do we do? Do we always do the best case scenario?
Not
When we're assigning a time complexity, do we say, hey, best case, it's this?
Worst case.
No,
Yeah,
Worst
it's worst case, right? It's always worst case. Because the worst case scenario, the 8's at the very end, which means we have to traverse through the entire singly linked list. If that's the case, if 8's at the end, or if we're just dealing with worst case scenario, can anybody tell me the time complexity of a singly linked list for just trying to find a value?
like constant.
O
What
of
do you mean?
n.
And no
O of n, right? It's O of n. Now let's talk about these two because I think this is really important. This is constant time. And this means that no matter how large my data structure is, it's going to take the same amount of time. But remember, time complexity is all just how much is your algorithm, or how long does your algorithm take as in is just an arbitrary value that represents however many values are in your data structure, or however many nodes we have, or how many, values are in my array. All it's saying is how long does it take to go through the, sorry, let me backtrack. When we're dealing with time and space complexity, the time complexity is how long does this operation take in reference to A being, 0 to infinite, right? And what we're saying with constant time is that it doesn't matter how large or how small, it's going to take the exact same amount of time. Again, if we're dealing with, 4, 7, 2, 5, right? And I want to get the, let's say let y equals this, and I want y of 1, right? I want to console log that. Well, it doesn't matter if, as long as there's 2 values in there, there could be, it's going to take the same amount of time as if there's 2 million values in there. Because it doesn't matter how large it gets, I'm still just going to look for this index position. and then I'm good to go. With this though, so that is constant time, right? The size of n does not impact how long it's going to take for this to run or for this to get the answer. Now, O of n means that the time it's going to take to run is dependent on how large n is, right? If there's 2 million values and I have to traverse through every one, and let's say the 8 is at the very end of 2 million values, I have to check 2 million values, which is going to take longer than if n were to have 12 values, right? And it was at the end. So however big n is, that's how long it's going to take for my algorithm to finish its whatever sort of calculation. And if you remember, we had this, that's what we call a linear, right? A linear, so it's time and then n. So as n increases, it takes more time.
I
That's
think
O of
I
n.
get I get that. Like maybe I missed the main concept for single list. I assume like for dictionary or object or array, like for object key value pair, and for linked list in elements in square bracket. Single
Mhm.
link is like as you showing me like the mechanism how we can get elements in the middle or swap or sorts thing. Like, did I miss like the main idea of single list?
A
That's
singly linked list is just a way that we can store pieces of information. And again, it depends on what you're doing and what you're trying to accomplish. But one of the powers is that, again, if we go back to that memory idea, and I'm not going to go through that again,
Yeah.
but an array, and I believe an object has to be consistent pieces of memory in order for it to save.
Mhm.
A singly linked list, all it needs is a pointer to wherever it's going to go. So if this is 2 and this is 5, and this is 8, it doesn't need to be consecutive. So it's really great from a space complexity, because I just need a point to 5, 5 points to 8, 8 points to 12, right? It's got a value that points to this memory. And so it's just another way to store data, but this is the main thing that's different. An array uses index position. This allows you to just use all you store is the value and where it's going next, which can have power. Again, it depends on the use case, can have power, or like we see, it might be a little bit more challenging. Again, it all depends, right? There's good times and bad times to use different data structures. That's why there's so many of them.
Okay, thank you.
Yeah, of course.
So
Cool.
if you have a number behind O, like you had O of 1, that's always going to be constant.
Yep, O of 1 is what we represent as constant.
Oh, it has to say 1.
Yeah, O of 1. So you're never going to have like a O of 3. It's just O of 1 represents constant time.
Okay.
Yeah. Okay. So we've done this, right? We've created our nodes and we built our list this way. But let's actually create a singly linked list, a true singly linked list within our actual, code here. And if I were to go to our login dashboard and I were to look at our projects and algorithms section, and we go to our singly linked list section, we see that a linked list really has two things, right? It's got a head and it has nodes. I mean, we don't really need to talk about the caboose here because not really kind of the point. It's just kind of the end, right? So when we're building a linked list, we're going to build out a class to represent our linked list, our singly linked list. So I'm going to delete this, and delete this. And then I'm going to comment this out so we can actually build this out. So I still need my node class, right? Because a linked list is consistent or is, consists of nodes, right? So I still need to have this. But now I actually want to create a linked list in itself. So I can say class SLL for singly linked list. And whenever I'm dealing with a class, what do I need to make sure that I add?
Constructor.
Yeah, a constructor. Perfect. Now this constructor doesn't actually need to have anything in there. Right? Because we're not passing in anything yet. I'm just creating a linked list. Now we're going to add nodes to this eventually, but what's just the main thing that my linked list has to have? If I'm looking at this photo here, what's the main thing? I'm going to add the nodes here, but what do I need to, what really is kind of the foundation of the linked list?
The data in the next.
The data in the next, those are of my nodes. So my node is going to have data and it's going to have a next value, but what does, kind of zooming out, what does my linked list have?
Head.
Yeah, exactly. My head, right? And so all I do here is I say this dot head. And at the beginning, it's just setting it equal to null, right? This is just an empty linked list. We don't have anything about it. I want to point out a linked list, a singly linked list does not have a tail, right? That's a doubly linked list, does have a tail. Cool. So I've created my singly linked list. And now I want to remember the power behind object-oriented programming is, can anybody tell me when I'm adding something under my class, what pillar of the OOP is that? Anybody remember? There's 4.
What's the question?
There's 4 pillars of OOP, and I'm wanting to put all of the code or all the methods associated in my class all within my class. What pillar of OOP is that?
Encapsulation.
Encapsulation, exactly, right? So I want to make sure that this is all associated with my singly linked list. Cool. So what I want to do is I want to add a node, right? I want to be able to add a node to my singly linked list. That node's going to have a value, right, that I pass in. And now I need to actually create some sort of methodology to add in my node, right? So what I first have to check is I first have to, when I'm creating this list or if I'm adding this list, what is going to be true if it's the first node that I have? I'm creating, so let me backtrack, sorry. I didn't ask that in a great way. I created this singly linked list, right? And all it has is what attribute? When it's created, what does it have?
The head.
Yeah, that's it, right? A head that's value is null. So I first want to check and say, well, is this the first value? Because if it is the first value, what do I want to do with it? Do I want my head to still be null?
You want to assign it to something, to the data probably.
Yeah, to my new node, right? So I want to say, hey, is this an empty linked list or is it full, right? And so first off, I need to capture the value that's being passed through, right? So let's say I was going to create this and I wanted to add the number 5, right? Well, I need to say let new node equal, and I need to actually create a node, right? And that node is going to be whatever value I pass in. So I'm going to say new node of value. And the same way that when I say node of 5 and it goes and it creates a new node with data and this dot next is null. Cool. Right? So we're just creating, we're basically taking it from down here to adding it here. Right? It's encapsulating within my singly linked list class. I'm still using the class node. I'm just taking it from doing it outside of the class of singly linked list into the class, right?
Add node is a class method.
I'm sorry?
Add node is a class method then?
Yes, it is a method of SLL of our singly linked list. So then we said that if it's null, I want to make my head this new value, right? So what can I check, or what would I do to kind of check to see if that's the case? I have a conditional check, right? So what if I say if this dot head equals null? Well, if that's the case, what's happening?
Gonna return the node. Or
It's not
let
gonna
the new
return-
node be assigned to
What's-
the value.
Yeah, when we're here, right? We've created our new node. It's just kind of hanging out, right? It's just chilling. Then we're first saying, well, hey, of this dot head of my singly linked list, is it empty? Because if it is, I want to do something. I want to assign it. I want
Is
to
The
say
first,
this dot head equals new node. Right? So, hey, if this is the first node in here, let's go ahead and make this the head. Now, what if it's not the first value? What do I
Say,
want to do?
you do dot next, this dot next equals, like if it's not null, then you wouldn't make it the head, you would make it the next.
Would I make it the next, or would I want to put it at, let's say I wanted to add it. I just wanted to add it in the same way that I add to an array. An array, I have 1, 2, 3. I want to add in the number 4. I want to add it right here.
Then you
So
should push it,
We've checked, yeah, but we don't have push, right? We don't have
'cause
that
it's a node.
with
not
a
an
node,
array.
yeah. So we've checked and we've said, nope, it's not the first value. So now what do I need to do in order to get here and find, well, where's the last value? Remember, with the single linked list, we don't know when that last value is.
so this dot next is gonna be the next node.
Yeah, so maybe I have an else. And then what I want to do is I want to say, I want to kind of figure out, well, what is the head, right? I need to start from the beginning and say, well, where am I going, right? I want to make sure I don't miss anything. So what if I said, we'll call this current node, and I want that to be equal to this dot head, right? This is, again, if this is not the case, if this is not an empty one, well, then I need to start from the beginning, and this node is the beginning, right? And this node is going to have what values?
Next.
It's going to have a next, and it's going to have my data, right?
Mhm.
Because each node has data in a next, right? Cool. So I'm going to say, cool, let's start at the beginning. And then I can say, while current node dot next does not equal, does not equal null, right? Then I want to do something. Well, all I'm wanting to do is I want to say, hey, is the next one null? And if not, then I want to say, is the next one null? And if not, then I want to say, is the next one null? And I want to keep doing that, right? So then all I'm going to do is, with my
Wow.
while loop, what's the main thing I have to make sure that I do? Always. When I'm dealing with a while loop.
You have to stop it.
I have to stop it. I have to have something in here to break this, or else I'll be in an infinite while loop. So I can just say current node equals, what do you think?
Null or next.
My next, right? So let's again think about this. We're sitting here and we're saying my current node is the head, let's say that I've got 1, 7, 8, and I want to add in the number 11, right? Oh, oops, I didn't mean to do that last part. 11. I'm gonna start here. This is my current node. And then I'm gonna say, hey, is the dot next null? Well, it's not, right? So then I want to move this to right here. And I want to say, well, my current node is this value. And I have access to this value within here by what? What is this node keeping track of? It's keeping track of my data, which is the number 1, and it's keeping track of my next value, which is the entire node of 7, right? Because it's pointing there. So I can just say, hey, I want to move from here, from this node to the next one. So I say current node dot next. And so now what it's going to do is it's going to keep going until it finds my current, and then it's going to come up here and it's going to say if current node dot next does not equal null. Well, this one it doesn't, right? Because the current node dot next is this node here. So then it's going to say, well, now my current node is current node dot next, so it's going to move it to the 8. And then it's going to say his 8's current node dot next null. And it is null, right? Which means it's going to break this. So now what do I want to do? I want to add this to the end. I've broken out of my while loop. What's my last thing I have to do?
Add the node.
Add the node. How would I do that? What do I have access to with just these 2 pieces of data that I can do?
New. This dot next equals new node. Something like that.
Very close. Very close. I've changed current node, right? And current node currently is 8, right? So then I can just say current node dot next. Remember, I'm still in the 8, and that is equal to my new node.
Okay.
so now-
why is it current node and not? Oh, I see the line now. Line 18. Okay, I got you. Thank you.
Mhm. Yeah, of course. So this is establishing this, right? And so then we are saying current node dot next. This starts here at the 1. When we break out of this, current node is now equal to this 8, right? And so 8 has 2 values. It has a data portion, which is the 8, and then it has a dot next value, which currently is null, which is why we broke out of this. So now we can just say, well, the dot next is now equal to this new node, which is this variable we created up here, which is our 11. And so now the next points to this node here. And so now we've added this to my singly linked list.
So
What is this?
I'm
ahead.
trying to understand on line number 15, the if condition, if this dot head equals to
Mhm.
null, that means like
That means my
the
singly
one.
linked list has no value. If it's null, the head is null, which is what we started with, right? Then
like node 1, right? That means
yeah,
like
no, we haven't started with node 1, right? So let's think through this. Let's pretend we don't have a 1, 7, 8, or 11. And let's say we're going to add each one individually, right? And we're adding the 1 here. It's going to come here. There's nothing in there. And it's going to say, let new node equal new node value in this 1 here. And it's going to say, if this dot head is equal to null, right? Are these the same, right? Which is going to be true because there's not currently anything in there. Then for the 1, because this is an empty singly linked list, it'll add and say, now the head is 1, or is this new node, which is our 1. When we go to add the 7, it's going to say, okay, well now new node equals the node that has the value of 7. And then it's going to say, if this dot head is equal to null, well, it's not, right? Because this dot head has now been, it was changed here to this 1. So it does not enter into here and it goes into my else statement. And it says, okay, well, great. I need to hold my current node as this dot head. And I need to say, while current dot next does not equal null, I enter into this while loop. But with the number 7, current node is this dot head, which is 1, and its value would be this next value is null, right? That's the only thing in there. So it doesn't even enter this while loop. So it says current dot node or current node dot next of my 1 equals my new node, which is 7. Then we add 8. It's going to check. It's going to add in 8. It's going to save 8 in this new node. It's going to check, hey, is there a head? There is. Then it's going to say, okay, we'll start at the head, go through. Is there a dot next? Well, there is a dot next, right? Because there's a 7. So it's going to enter into this. And now it's going to say, okay, we'll go from the 1 to the 7. It does that. And then it says, does 7 or the node that has 7, is its dot next value not equal to null? Well, it is equal to null because there's only 2 things in there. So then it exits my while loop and it says, okay, well, 7's dot next value is now my 8. And so it just keeps doing that. Does that make sense? Does that help?
Yeah. Yeah, I get the first if condition, like we create a new node, and on the else condition, like when on line number 18, when we say current node equals dot head, means like it's breaks the if condition because this dot head is equal to now. It's not. There is this dot head, which is number 1, right? But on else condition, line number 18, current node equals this dot head means it's referring the current node is 7 or 1 on line number 18.
18 will refer to the 1 there.
Or current node is
This
7.
dot head. No, current node is this dot head,
Oh, not 1. Okay.
which would be
So-
my 1. Now remember, if this is not true, it goes here. So it doesn't enter in and change the new node. This is only if this is true, which is only true upon creation. And then once a new node is added, this is never true again. So it jumps into here.
Okay.
Remember your if else, it's binary.
Right.
If
Okay.
this is true, then it jumps in, else it jumps into something else.
Okay. So on line number 18, the current node refers to node 7, right?
No,
Node
current
1.
node refers to this dot head of my singly linked list, which will always be 1. If 1, in this case, 1 comes in again, remember, let's say we add an empty list and I add in 1, right? I'm saying add node and I do it for 1. It's going to check and say if this dot head equals null, which is true, right? Because it's an empty list. Then it's going to say, well, now the head is the new node, which is 1. I go to add the 7, it's going to say if this dot head is equal to null, which is not true because it's equal to 1, right? So then it comes down here and it says, well, let current node, we have to start from the beginning. I want it to be equal to my head, which is 1, and then it iterates through.
Okay. Okay.
Does that make
Oh,
sense? If
yeah.
not, we can talk after class or I'll make sure that you get it if it's not clicking.
Okay.
Cool. Any other questions on this? Anybody tell me the time complexity of something like this?
Time complexity of the class singly linked list or of add node.
Of add node, sorry.
O of n.
Yeah. Yeah, right, because you have to, worst case scenario, you start from the beginning, you have to go as long as it is, right? However long it is. Good job. So that's if we want to add a node to the back. What if I wanted to add a node to the front? And this is where the power of singly linked lists can be, right? If I am creating a playlist and I'm like, oh, I want to add this to the queue, like Spotify has like the queue, You can just add it, this kind of thing. If I want to add to the front, way
Oh, one.
easier. Right? So if I want to add it to the front, I still need a value that I'm adding. But all I have to do is I have to say, well, let new node equal, and I say new node value, right? Still same thing. I'm still creating an instance of node there for my new value that I want to add to the front. And then all I say is new node dot next, because all of anytime I create a node, it's got a this and a next equals this dot head, right? So now I'm creating a pointer to the head, and then all I say is this dot head equals new node. Oops, not that. New node. That's it. That's all I do. I'm just changing the pointer to, I'm saying, hey, you know what? Instead of 11 being kind of the end and 1 going there, I actually want 11 to be the beginning. I want to point it to 1, and then 1 can point to 7 and 7 can point to 8. Right, but now 11 is my leader, right? And I could actually just take it and move it and say, well, I want, of course it's gonna make me go, I'm just gonna delete that part, but so nope, I just want it, and I just change the pointer. It's really, really simple. I say, there, I'm just putting it there.
So this is when you would want to use a singularly linked list. It's
Yeah,
when
it's
you
easy.
want to be able to add to wherever.
Yeah, or if I'm like removing things, like let's say I've played a song, like think of Pandora, and I've got this list of things and I just want to remove from the beginning, like an array. If I have an array, and I, have like, 11, 1, 7, 8. If I'm just popping even from the front, right, the song's played, I want it over with. Well, I create a copy under the hood. You create a copy of this, which is time and space intensive, and then you create a new, you create this copy, and then you find another thing, and it's like it's quite a bit versus I just get rid of the front, and then it's very simple to handle. Now my head is right here, and that's it, right? I just say, well, hey, now the head's here, and we get rid of this value.
So do we use single lists for like swapping elements or searching items, or ordering, like sorting stuff? We see here like adding nodes.
No, not necessarily. There's different things you can, there's a million different sorts you could do, or if you're searching through things, you can use like binary search trees using breadth for search or depth for search. So there's different things. Again, there's so many that we'll talk through, and things we won't even get to because it is a very robust thing. But we're dealing with singly linked lists. We'll deal with recursion. But here are these trees where you can do these are binary search trees. And so this is where if we're like searching for something, if we're trying to find a value for something, and there's queues and stacks. So the real thing to think about, like a singly linked list, would be like the perfect example is dealing with music, right? If you're queuing something up next, right? I know there's a queue, but if you have like, I want to create a playlist, or I want to create my favorite things or my perfect day, you might have a singly linked list, because then you can alter and say, well, instead of having breakfast here, I want to have breakfast here. But if you're storing the data, you don't have to go in and, save it in some different way. You just kind of, okay, I'm just going to swap that out. It's a lot easier.
Thank you.
Yeah, of course. Okay. So we've talked about adding nodes to the front and to the back, but what if I wanted to remove nodes? Again, still pretty simple. So if I want to remove front. Let's say I just want to remove from the front. Well, I need to know, I don't really need to know anything, right? I just need to take out the value from the front, right? I want to get rid of the song has played. Now let's get it out of our linked list here. So all I would do is I would just say, hey, I want to change the head, right? If I've got that, again, we'll take 11, 1, 7, 8. And my head is currently on my 11. Well, now I just want to change the head to here, right? And say, I just want you to care about this. Now we're not going to say it's dot null or equal to null because then we kind of lose the rest of this, right? But let's think of what we can do. Let's use our caps for our OOP knowledge from back in Python or our old OOP knowledge and think about what can we do. So first off, I want to make sure, hey, is this the, as long as it's the last one, right? I want to make sure that there's nothing, if I'm doing remove from the front, I want to make sure that, hey, it's not empty, right? So I can just say if, and I can say this dot head is not equal null. Well, then what do I want to do, right? I want to make sure it's not already empty. If I'm going to run this method, I just need to build in that edge case. If it's not null, meaning that there's a value there, then all I have to say is this dot head equals this dot head. And what does, if you guys remember back from Python, we did a users with bank accounts assignment, and we learned about something called a chain method, right? Where we could chain methods together or dive into different parts of a class, right? So my head represents a node, right? Because my head is this entire node. And this node has properties. Your super close colon, it has properties, and it has two properties, dot data and dot next. Right? So I can say this dot head is this dot head dot next. And then now I have removed the head from being 11, and now it goes to 1. Right? And then worst case scenario, it was null. And so then now this dot head equals null, and I officially have an empty singly linked list. Now my list is done. Any questions on this? On what we talked about?
How we add nodes in between different nodes?
I'm sorry, what do you mean?
Like if we want to add a new node in between rather, or this is just to add. I thought this is just to add node in at the where.
This is
Okay.
within my singly linked list. So I could say something like new, let singly equal new singly linked list, right?
Mhm.
In the same way that I had this value here. And so now singly has different things. And I can say singly dot add node. And what do I want to add? I want to add 11. I want to add 1. I want to add 7. Oops. Sorry, my hotkey is different. And I want to add 8, right? So now this has added all of my values. And let's see if we can console.log singly. Okay, see what this does. Cool. So my singly linked list has a head of with this node of 11. Its next node is 1, and then it keeps going. It doesn't show it, but it keeps going. because this has the next node and then so on. It's just truncated because of console log. Oh, did I freeze there? Okay. So now we're able to add, or I could say, let's try this. Let's do, okay, so we saw that, but I want to say singly dot add to front. I want to add the number 96, 98. And then I want to console log singly. Cool. So first we'll see that the head is the node with 11. We added to the front, and so then we should see that the head is node 18. Yep, so we get 11 and then 1, and then now we see it's 98, which then points to 11, which means that we're able to add in, hey, we were able to add this to the front. I want you to play this next, kind of thing.
Can we add 5 in between like 7 and 8?
You would have to have like adding to the middle
Or the method,
or the what, I'm sorry?
the class method? You mean like we need to
Yeah,
add
so
before middle? adding
sure.
all-
So we would have to do a couple things, right? Where we would have to first, because a singular linked list doesn't have the built-in properties, like an array has the length, right? And so I could just say, array dot length over 2, and that's my half, and I could, use like round or mathlore up to get the whole number, and then I say, okay, at this part, I want to put it in the middle, so then it, I can add it at that index and then kind of shift everything over. This doesn't have that. So if we wanted to go through the middle, first I would have to see, well, how large is this? So I could say something like list size. I don't know that we'll even be able to kind of handle that at the beginning. And at first I'd probably actually just have to count. So I'd say let count equals 0. Right? And then I'm going to, again, start at the beginning. Let current equal this dot head. And then I'd have to iterate through and then say while current does not equal null, say count plus, right? And so I'd get this count and I'd return that. Oh, and then I need to, ooh, I almost broke my own rule. And I say current equals current dot next. So then once I've done that, and I have that current number, I could say return count, because it's done, right? My current is null, or once it gets to null, that means I'm done. So I now have this count. So then what I could do is I could say something like, I would need to get, so we'll just do, I'm just doing this off the cuff, so bear with me here. I want to give a value. I want to add a value to the middle, right? And so first I'm going to say let new node equal new node of value. Then I would call list size. This dot list size. It's a count equal this dot list size. Then I would say, okay, great. I want this list dot this size over 2, right? Because I want it in the middle. And then after that, I would, let's see. I would then iterate through and say let current equal this dot head, right? And then I would say while we'll say, I'm going to call this, sorry, We'll call this middle. Then I'm gonna say let count equal 0. Then say while count is less than middle. Then I want to say current or count plus plus current equal current dot next. Once that's done, that tells me that I'm in the middle. And then I would say current I would want to keep track of the next value. So I'd say next node equals current dot next. And then I would say current dot next equals new node. And then lastly, I would say new node dot next equals next node. And then this would put it in the middle of this. So we would have to first determine the middle. So we iterate through the whole thing, take a count. And once it's done, we return that count. We add a add middle method where we take in the new node, we make a new node of whatever we want. We determine the middle, and that's whatever the list size is, because remember, whatever it returns, that's what this gives us. If I need to do this or not, I think so. Whatever this returns, that's what's going to give us. And so it's going to return that. So middle is going to be equal to, let's say this is 6 divided by 2. So middle is going to be equal to 3. We say current, we're starting at the beginning. We're starting count at 0. And we're saying, hey, as long as count is less than 3, meaning that we're not in the middle yet, well, then I enter into my while loop, my count increases because now it goes to 1. And then I move my current to the next one, right? And I just keep going. Once I break out of this, that means that it's no longer less than 3, which would tell me that we are at, our current is the node that's kind of right before the middle. And then what we do is we capture the value that the current node has that it's currently pointing to in this new node is the current.next. We re-evaluate the current.next and say, well, now I want to insert my new node. And then lastly, we make the pointer and say, okay, now take this new node dot next and move it to the middle. So if we were to kind of visualize this, let's pretend we had 2, 4, 5, 6, and I wanted to add in the number 7. We're going to get how many values there are. So we're going to get a count of 4, right? Then we're going to create 7. And count of 4, middle is going to be equal to 4 over 2, which is 2. Current is going to be on the head. Count is going to be equal to 0. Once we go in, count is at 1, right? Then we move it over to 4. Once it enters 4, count is at 2. And we still are good to go there. Then what it's going to do is it's going to break this because now count is no longer 2. And so then we are trying to think if this is going to work or not. Or else if it gets to 2 and then it goes to the next node. We'll figure it out. And then we basically here, if these are all pointing at one another, I'm going to save the 5, the pointer, and I'm going to move it to 7. And then I'm going to take that value and make this point to 5, just like that. Does that make sense? I know that went a little bit over time, but does that make sense?
Yeah, it does. Thank you.
My only thought would be if this, while count is less than middle, count is starting at 0. So if we go up to 1, but we're starting at 1, so count should actually start at 1. We're starting on the first value, right? And then it's gonna go current equals current dot next, or else what would have happened if I would have started at 0? Then what would have happened is I would have gone from 2 to 4. And then, or I would have started at 2. And then I would have added +1, so count would have been at 1. And then I would have moved on to 4, and is 1 less than 2? It is. So then it would have gone up to 2, right? And then it would have moved it to the next one, so it would have been 1 off. But with a raise, we start at 0. This, we can start at 1. And so this would work. Any questions on that? It's kind of off the cuff, probably a little more advanced than you guys needed right now, but that's how I would approach it. Did that help? Cool. Okay. That's all I have. Tomorrow we'll continue with singly linked lists. We're going to keep building it out. We're going to keep just practicing. We'll do like, how do we remove from the back? How do we, kind of deal with displaying them? And then maybe we'll look at doubly linked lists as well. So we'll see. Cool. Other than that, I will stop the recording here, and I hope you guys have a wonderful night. Please don't forget to send me your group stuff if you want to be in a group.